Good evening. Thanks for attending to my presentation. My name is Pedro Jäger, researcher at the Lab Solda, Welding and Mechatronics Institute. And now we'll be talking about the conception of an algorithm dedicated to optimize the overlapping of welding beads for the wire and arc additive manufacturing. One of the challenges of wire and arc additive manufacturing is to predict and control the deposit geometry. When the desired part has wide sections or even bulk characteristics, like in the figure 1, there is a need to do overlap multiple beads to create these wide layers, similar to what is done in cladding applications. The challenge is to achieve a flat and smooth surface that will be subsequently the base for the next layers. Uneven surface may lead to the accumulation of errors in the vertical direction. After the deposition of several layers, this error is summed, and when it's not in consonance with the thermal gradient, the heat input, and many other parameters involved during the welding process, it can lead to huge effects in geometry of the welding beads and the part being built itself. As the figure 2 and 3 show, the cross-section profile of a single bead can be represented as a parabola function by means of its height and width. From these inputs of height and width, assuming that the weld bead width represents the intersection of the x-axis and the height represents the maximum value of the parabola, a regression analysis is performed and a quadratic function is created. So as the figure 4 represents, after creating the first function, a second function similar to this first is created, but with a horizontal offset. For optimal surface smoothness, the areas C and D must be the same. So the same material volume would occupy the C area that would occupy the C area goes to the top, the D area, the valley. According to this statement, the algorithm tests multiple offsets until the difference between the areas goes to a minimum. So from that conditional loop, center distance among the maximum values of the parabolas is defined. To explore center distance effects and the resulting layer quality, experiments changing the center distance were realized. The first was proposed to decrease the center distance in 10%. The second to increase 10% in the center distance. So the practical experiments were made for those three center distance, and its cross-section profiles analyzed by micrography. So we cut the plate and analyze its cross-section and measure the width, the height, to compare with the simulated results. From the single bead profile measurements, the offset of 5.22 millimeter was calculated by the algorithm. The simulated and overlapped deposit profiles differ in width only 0.25 millimeters, about 2% of error between the values. These results show a good accuracy of the algorithm, corroborating with similar studies that used similar method with second-degree functions. However, the welding defect of lack of fusion between the beads is noted, which may be caused by incorrectness of the center distance. By decreasing the overlap offset in 10%, it was possible to mitigate the lack of fusion defect observed in the previous experiments. In this case, the second bead height was almost 1 millimeter higher than the simulated, which is expected once we decrease the offset. However, the width presents a difference between the simulated and deposited of less than 1%, showing again a good precision of the algorithm. By the other hand, increasing the overlap offset in 10% caused more more severe lack of fusion between the beads. We can see here it's a little bit bigger. So this results shows a relationship between the increase of the offset and the formation of this defect, possibly influenced by the way of anchoring the weld pool of the overlapped bead on the base bead. Analyzing the proposed method, it was verified a good approximation among the simulation and experiments, with error less than 1% for width and 2% for height. However, for a good weld quality, it was necessary a reduction of 10% in the center distance. In general, the optimal center distance calculated using the proposed method corroborated with similar works referred in this paper, that also found center distance values around 67% to 73% of the base width. This fact shows that it's possible to accurately and precisely use second degree functions to represent weld seams, even though that in some real cases the overlap bead height may vary somewhat. In addition, 3 overlapping weld beads were deposited. The results corroborate with the previous experiments, where for the case A and C, lack of fusion can be seen. In case B, using the nominal distance minus 10%, the effect of lack of fusion was avoided. The height deviation was noted for all cases about the same value of 15% or 0.45 millimeter. However, in the case A and C, a higher value is seen in the top of the weld beads, which is not so eminent in the case B. So the case B showed the better surface smoothness. So we can conclude with this paper that it is possible to represent weld bead profiles with accuracy less than 2% of error using the second degree functions. The overlapping method, considering the valley area and the overlapped area, is functional and represents the real case. The lack of fusion increases as a function of the center distance growth. So it was evaluated that decreasing the center distance for values less than 10% of the nominal calculated distance will mitigate the effect of lack of fusion without any significant geometrical variation. The center distance among overlap beads can be from 60 to 73% of the welded bead width, corroborating with the related studies evaluated in this paper. However, the present study evaluated that the great center distance, or the best center distance, is about 60% of the welded bead width, which decreases the defects that we could see in the other experiments. Thank you very much for attending to my presentation. See you.